Welcome to this explainer. Today, we are stepping straight into the newsroom of Cambridge Physics, specifically targeting syllabus code 0625. We are looking at the fascinating mechanics of balance, turning forces, and stability that dictate our physical world. But listen, we aren't just casually chatting about physics today. We are analyzing this through a high-stakes, high-pressure lens, mastering the Cambridge exam under strict deadline pressure. The clock is ticking in that exam hall. You need to break down the story, which is your question, and deliver the headline, which is your perfect, mark-winning answer. Now picture two students sitting in that exam hall right now. First we have Alex. Alex is brilliant but panics, overloading their paper with raw physics facts, completely ignoring the command words, and offering zero actual analysis. Then we have Sam. Sam rushes. Sam constantly misses the core requirements and throws away easy marks. Throughout this explainer, we are going to put their flawed answers side by side, strip away the red pen marks, and show you the exact blueprint to secure top marks. Let's get into it.
Okay, let's hook straight into a classic Cambridge challenge. It looks so simple, right? Why is a door handle always placed on the opposite edge from the hinge? But in an exam setting, it is a trap if you aren't prepared for what the examiner actually wants. Let's look at how our two students tackle it. Alex sees the word door and writes a massive, sprawling paragraph about friction, air resistance, and energy transfer, completely missing the core point. The examiner gives that 0 marks. Sam, feeling the time pressure, just scribbles because it makes it easier to open. Again, 0 marks. Look, easier is not a physics term. The examiner is looking for the headline here. To get the green check marks, you need to deliberately name the physical forces at play and structure your answer precisely.
Here is our strategic roadmap for today's session. 1. The turning effect. 2. Calculating the moment. 3. The principle of moments. 4. Finding center of gravity. 5. The science of stability. And 6. Real-world balancing acts.
Section 1. The turning effect.
Take a look at this. It brilliantly illustrates the physics in action. Picture a person pushing a door. This is exactly the scenario you need to visualize for that door handle question we just looked at. Now I want to introduce you to a framework that top-tier students use. It's called PEAL. Point, evidence, explanation, link. First, the examiner wants to see your point. You must identify the pivot, which is the fixed hinge. Next comes your explanation. To open the door effectively, you must push with a force as far away as possible from that pivot. The door handle is deliberately placed at the opposite edge to maximize this perpendicular distance. Furthermore, notice how the person pushes at right angles to the door. Pushing at any other angle instantly gives a smaller turning effect. If Alex and Sam had just stopped, breathed, and focused on maximizing the turning effect by maximizing the perpendicular distance from the pivot, they would have secured full marks instantly. That is how you turn a messy answer into a clear, undeniable headline.
Section 2. Calculating the moment.
The absolute crucial concept here is the formula itself. The quantity that tells us the turning effect of a force about a pivot is called its moment. The equation is incredibly strict. The moment of a force equals the force multiplied by the perpendicular distance from the pivot. Let's talk serious exam strategy for a second, because this is where Sam always loses points. You must look at the units. The unit is the Newton multiplied by a meter, giving us the Newton meter, or capital N lowercase m. A classic, almost guaranteed examiner trick is to give you the distance in centimeters. If you rush like Sam and just multiply the numbers without converting those centimeters into meters first, you lose the accuracy mark immediately. Always decode the data provided before you touch your calculator. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 3. The principle of moments.
In science, when things are perfectly balanced, we say they are in equilibrium. But listen closely, because to get the marks for defining equilibrium on a Cambridge paper, you need two very specific conditions. You can't just say it's balanced. First, the forces on the object must be balanced, meaning there is 0 resultant force. Second, the turning effects must be balanced, meaning there is 0 resultant turning effect. And this brings us directly to the principle of moments. An object is in equilibrium when the sum of the anticlockwise moments about any point exactly equals the sum of the clockwise moments about that exact same point. If you just write down the moments are equal, you will likely miss the mark. Examiners are ruthless about this. You must explicitly specify the words sum of clockwise and sum of anticlockwise. This level of precision is exactly what transforms a flawed red ink answer into a perfect green checkmark masterpiece.
Notice exactly how this principle looks out in the real world. We have a father and daughter balancing on a seesaw. On her own, the daughter's weight would make the seesaw turn anti-clockwise. To balance her out, the father pushes down on the right-hand end, applying a clockwise moment. Because the father has a significantly greater weight, a greater downward force, he must sit much closer to the pivot to create an equal turning effect. A lighter person sitting further away perfectly balances a heavier person sitting closer. Now, Alex would see this and write a whole page on gravitational fields. Don't do that. Keep it tight. This is a standard calculation question waiting to happen. So how do we ensure we get every single mark without panicking when the timer is ticking down? I'm going to walk you through our foolproof three-step system for calculating unknown balancing forces. This is your physics success blueprint. Step 1. Do not touch your calculator yet. Write down exactly what you know and what you want to find out right there on the paper. List the anti-clockwise force and distance and the clockwise force and distance. Step 2. Write down the explicit statement. Total anti-clockwise moment equals total clockwise moment. Do not skip this. Writing this foundational physics principle down often secures you the first method mark, even if your math goes wrong later. Step 3. Substitute your values and solve for the unknown, making absolutely sure your final answer has the correct units attached to it. This structural system completely prevents the rushed, sloppy mistakes Sam makes, and it actively forces Alex to stop rambling and provide the actual physics that answers the question. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Finding Center of Gravity. Okay, welcome to the interactive workshop segment. We are under the clock here. Challenge 1 is a data scan. What is the exact Cambridge-approved definition of the center of gravity? Scan your memory right now. You have seconds. Got it? It is the single point at which all the mass of an object could be located, and the object would behave exactly the same. It's the point where its weight acts. For a perfectly symmetrical object, like a uniform meter ruler or a solid ball, that point is dead in the mathematical center. For a human being, because of our general symmetry, it lies roughly in the middle of the body, right around the navel. Knowing this specific definition verbatim, word for word, is an incredibly easy way to pick up a quick recall mark when you're under deadline pressure.
All right, time for Challenge 2, Find the Flaw. We have an explanation from Alex on how to find the center of gravity of an irregularly shaped piece of card, often called a plane lamina, using this specific experimental setup. Listen closely to Alex's answer and see if you can spot the flaw losing him marks. Alex writes, you punch a hole in the card and hang it on a pin. You draw a line straight down. The center of gravity is on that line. Okay, time's up. What did Alex miss? The examiner is only giving 1 out of 4 possible marks for that. Why? Let's break out the green pen. First, you must explicitly state that the card is suspended so it can swing freely on the pin. Second, you can't just draw a line straight down. You must mention using a plumb line, a weight on a string, to accurately mark the vertical line. And the fatal flaw? You have to repeat the entire process for at least 2 more pinholes. The center of gravity lies at the exact mathematical point where all 3 of those drawn lines intersect. That is how you decode the command words and turn a measly 1-mark answer into a flawless, examiner-pleasing 4-mark procedure.
Section 5. The Science of Stability.
Now for Challenge 3, Speed Writing. We are going to build the perfect Peel paragraph. Compare these 2 glasses. A tall glass can be knocked over quite easily, right? It is inherently unstable. Why? Well, in the upright glass, the weight acts straight downwards from the center of gravity, and the contact force from the table acts straight upwards. The 2 forces are perfectly in line. They're in equilibrium. But when the glass is tilted past a certain critical point, look closely at the line of action of its weight. The glass topples the exact millisecond its center of gravity shifts so that the line of weight falls beyond the edge of its base. Memorize that exact phrase, beyond the edge of the base. At this specific point, there is a pivot created where the edge of the base touches the table, and the weight creates an unbalanced clockwise moment. That resultant turning effect is what aggressively tips the glass right over. If you use the technical terms line of action of weight, pivot, and resultant moment, your paragraph will be completely bulletproof.
Let's summarize our final system for stability into a quick cheat sheet you can use on any exam question. An object that is incredibly unlikely to topple over must have 2 distinct features, a low center of gravity and a wide base. Think of the ancient pyramids. Their geometric shape inherently gives them a massive, sprawling base and places their center of gravity incredibly close to the ground, making them virtually impossible to tip over. Conversely, an object is highly unstable and likely to topple if it has a high center of gravity and a narrow base. This is the core data trend you can apply to absolutely any complex chart, graph, or weird diagram the exam throws at you. So remember our 3 rules that guarantee top marks. Rule 1, command word decoding. Rule 2, PEL framework application. And Rule 3, the time management matrix, always write your knowns and unknowns first so you never rush the math.
Section 6, Real-World Balancing Acts.
Look at this phenomenal application pulled straight from the syllabus material. This isn't just a bit of fun movie trivia. This is pure high-stakes physics in action. We're looking at the famous cliffhanger bus scene from the classic 1969 film The Italian Job. The getaway bus is hanging over the edge of a massive vertical drop, balanced precariously. Now, in the real world, double-decker buses actually undergo extreme tilt testing to an angle of at least 28 degrees just to ensure their center of gravity doesn't fall outside their base. But in this cinematic scene, the bus is effectively acting as a rigid beam pivoted right on the edge of the cliff. The massive weight of the bus engine at the front provides a stabilizing moment, while the gang and the heavy stolen gold at the back provide an opposing turning effect. Shifting even a tiny amount of weight towards the back of that bus will move the overall center of gravity just over the cliff edge. That creates a resultant turning effect that will send the entire bus crashing down the mountain. This brilliantly illustrates how multiple moments work simultaneously on either side of a single pivot.
So, putting yourself in the shoes of a Cambridge top-tier student, knowing the principle of moments inside and out, how would you save the gold without tipping the bus? What is the mathematically correct, perfectly balanced physics solution to this cinematic cliffhanger? You'd have to incredibly carefully manage both the clockwise and anti-clockwise moments to maintain that delicate equilibrium. Think about it and see if you can apply these exact principles yourself. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.